Hi folks, Mr. Comer here. I hope you enjoyed the crash course video above. If nothing else, I think it really does help you to understand the physics equations that are behind so many of the devices that we use every day. Your phones, computers, televisions, all of them have circuitry inside them, and all of them follow these rules. Don't get overwhelmed by some of the example problems that Dr. Samara worked on. We won't be doing anything too intense along those lines, but I do want you to see how she used Ohm's law to answer circuit analysis questions, as that's exactly what we're going to be doing for this assignment and for the lab, which is our next assignment. So for what I want you to do right now, we're going to be doing some current calculations and complete problem 1 on positive physics. So to be clear, that's the section that's called current calculations under the section that is the unit that is circuit analysis, and the section that is complete problems 1. Okay? That is 2 sections. It might sound like a lot, but it's actually only 7 questions in total. The first couple questions, the current questions, go by pretty quickly, and then the complete problems 1 are a little bit more extensive, so there's only 2 of those. So 7 problems total, not too bad. Right now, I'm going to do 2 example problems with you using Ohm's law to show you what you need to do. All right, so let's do an example problem from the current calculation set. First, we need to make sure we know what equation we're using. In this case, it's the same one that Dr. Samara was using in her videos, Ohm's law, right? So I wrote it at the top right here. Voltage is equal to current multiplied by resistance. That's the only equation we're going to need in this problem set. Let's look at the circuit and do some quick analysis just to make sure we know what we're dealing with. So let's point out the pieces first. Here's a battery. It's providing 12 volts of pressure in this circuit. Okay? We've got a junction in this circuit line, so we know the whole thing isn't series. We've got a parallel break right here. Okay? In this break, there are 2 resistors in series with one another, one of which is 10 ohms, the other of which is 30 ohms. Then we've got over here on this parallel line, one 10 ohm resistor. Okay? So 3 resistors, 2 in series. The other one is in parallel with those ones. Okay? How would I describe this? Well, this is what we'd call a combination circuit. It has both resistance in series and resistance in parallel. Great. Well, what do we know about circuits that involve a parallel break? Voltage stays the same, current changes. Okay, so if 12 volts is supplied to this battery, going around the circuit, that means 12 goes down here, and 12 goes down here. Let's start with the more complicated one over here. 2 resistors in series with one another. Well, if they're in series with one another, we know that the voltage is going to drop across both, and it will drop across both unequally. But we don't really care about that right now. All we've been asked to find is the current. So let's not focus on that. Let's focus on, we know that the voltage must be equal to the current multiplied by the resistance. In this line right here, we know the voltage, and we know the total resistance. 10 ohms plus 30 ohms means that this line has a total of 40 ohms on it. And this one, of course, has a total of just 10 ohms on it. Okay? Well, we want current. How can we switch up this equation to make it for solving for current instead of for voltage? Divide both sides by resistance. Great. Current is equal to voltage divided by resistance. Over here, we've got 40 ohms, and we know that the voltage is 12. So 12 divided by 40. Over here, we've got 10 ohms. The voltage is 12, so 12 divided by 10. Well, 12 divided by 40 is 0.3 amps. And again, we know, based on what we've seen in the videos before, current, right, in a series stays the same. It's voltage that drops down. So since these 2 are in series with one another, the current must be the same for both of them. There's a total amount of resistance, 40 ohms, total amount of voltage, 12. 0.3 amps must be for both of these. So that must be what the amperage is in A, 0.3 amps, and that must be what the amperage is in B, 0.3 amps. What about over here? 12 volts, 10 ohms, 12 divided by 10, 1.2. 1.2 amps across C. Well, Mr. Comer, how are we supposed to figure out how much current is actually coming out of the source battery? Well, now that we know how much is going through this line and how much is going through this line, remember, in a parallel break, voltage stays the same throughout both, but amperage changes. It splits into both lines. So if we know there's a split in the amount of current here, whatever was here has to be the same as whatever comes out of the two lines reconnecting once again. So if 0.3 amps goes through here and 1.2 amps goes through here, what's 0.3 amps plus 1.2 amps? 1.5 amps. That must be the source amperage coming out of the battery. That's how we answer current problems. Seems like it's complicated at first, but all you need to do is take it step by step. Look at how much voltage is coming out. Remember, in series, current stays the same and voltage drops down. But in parallel, like this split line right here, voltage stays the same and current is the one that changes. As long as you keep that in mind, the math involved here is very simple. We're only using V equals IR for the current calculation problems. All right, those problems, again, pretty straightforward. Do the same thing we just did right here. The complete problem set problems that make up the next set are a little bit more complicated, so I'd like to do one of those. These problems require you to do one extra equation, and they involve finding out things more than just current, okay? So here's an example problem from complete problem sets 1. Your problem will probably look almost exactly like this in terms of what the circuit layout is. What will be different is the numbers. So don't take these numbers as exactly what you should write down. Your numbers will be different. But let me walk you through the calculations, okay? The first thing that this problem set asks you on positive physics is, well, how many routes are there to take? Well, that's easy enough to calculate. We can see that we've got a battery right here. Go along the journey. Oh, we've got a split. It could go this route to return to the battery, or it could go this route to return to the battery. That's 2 routes. Great. 2 routes in this circuit. Next question that I ask you is this a series circuit? Is this a parallel circuit? Or is this a combination circuit? Well, much like our previous one, this is a combination circuit again, right? We've got 2 resistors that are in series with one another, and we've got a resistor that's in parallel with the rest. That's a combination circuit. So, combination circuit. Done. Another thing that the complete problem set asks you is to please use the units in each one of these symbols. So what you're trying to calculate is the resistance, the current, the voltage, and the power. We need to put it in the correct units. Well, the units in resistance are ohms, right? So we'll put in ohms right here. Should be down near the bottom of the little scroll chart that pops up. It's the Greek letter omega. It's their final letter, in case you've ever heard the term alpha to omega. Alpha is the first Greek letter, omega is the final Greek letter. So you'll see it down there around Z and V and things like that. What's the symbol for current? Remember, it's named after ampere. It's amps, amperage. So we've got our A right there. Voltage is named after Volta, who is an Italian. I called him French in my last video. And that's another V, right? The volts in a circuit. Finally, we have power. Remember, power is very similar to the power that we were working on in our assignment with work. Power, moving up the staircases, that's watts, okay? So we'll draw on our watts there. There's all the units that we have. One thing we will not need to calculate is the resistance inside the source, the battery. Technically speaking, there is a small amount of resistance in all sources. It, by definition, is designed to be as small as possible, so as to allow as much current and voltage out of the battery as is possible. In this case, much like with friction, we're just going to ignore it. It's so small that we don't care about it right now. If you were doing really delicate electronics or you were trying to develop a new battery, you'd care about the resistance inside there. For our purposes, doesn't matter. All right, let's try and tackle this problem. We're going to start tackling this the exact same way that we did with the current problems. It's just that we're going to take it a little bit farther. So let's start off same way we did before. We know that 6 volts is going through this line. At this parallel break, according to the law of circuits, we know that 6 volts must go down here, and 6 volts must go down here. It's the current that will be different. So, a line, 6 volts down this way, 6 volts down this way. Don't know how much current is going down these lines yet, but it's pretty easy to calculate. We know the total resistance here must be 20 ohms, 10 ohms plus 10 ohms. Total resistance on this line must be only 10 ohms. Okay? How do we calculate current? Remember, Ohm's law. V is equal to current multiplied by resistance. In this case, we're trying to find current, so we take voltage and divide it by resistance. The voltage here is 6 volts. The current on this line is 20 ohms. 6 divided by 20 is 0.3. So 0.3 amps. What about on this line? 6 volts divided by 10 ohms is 0.6. I'm going to draw this over here so my head doesn't cover it up. That means 0.6 amps. Okay? Current is going to be the same across series. These two resistors are in series, so we know that the current across A must be 0.3 amps, the current across B must be 0.3 amps, and the current across C must be 0.6 amps. Just did those calculations right there. Great. Same thing with current calculations. How do we find the source? Well, if 0.3 is coming out of here, 0.6 is coming out of here, those join up, the current from the source must be 0.9 amps. Now, we didn't do resistance yet. We might as well do that. Thankfully, that's pretty straightforward. It already tells us what the resistance is right here. We didn't have to calculate it. A was 10, B was 10, C was 10. 10 ohms for each one. Great. What about voltage? Don't we know the voltage already? Well, we know the voltage that's coming out of the battery, and we know that 6 volts is going down each one of these pathways, but what we don't know is how much is actually hitting each resistor. It's easy for this parallel break right here. There's only one resistor here, and if 6 volts is coming down this line, all 6 volts must be going into that resistor and being dissipated by it. So that means that we know how much is going through C. It must be 6 volts. But what about here? How would we figure this out? Well, thankfully, in this specific problem, it's very easy because both of these resistors are the exact same resistance. And remember that voltage drops proportionally across resistors. So if we have 6 volts, and it has to drop proportionally, 10 ohms here, 10 ohms here, it's the same. 3 volts is going to go across each resistor. 6 plus the 3 plus the 3 is our total. That's 12, that's 6 volts total because the 3 went across here. So we've got our 6 volts in our battery. Okay? Now the voltage doesn't add up entirely because remember, it has to split. What we need to see is 0 coming out of each one of these junctions as it makes its way back to the battery, not 0 on the entire circuit, right? Because even though there's 6 volts in the start here, it doesn't split 3 and 3 in each side. That's not the way that circuits work, right? Voltage splits evenly across junctions like this. So this 6 had to be dissipated 3 here, that's 0 at the end, and then the 6 went away here, 0 at the end. We've got 0 voltage going back into the battery, okay? This problem would be a little bit more complicated if one of these resistors had more or less than the other resistor. Because in that case, what we'd have to do is use Ohm's law to determine the resistance. And that's pretty easy. I can show you how to do that right here. If we know that 6 volts is going across this, right, and we know that the current involved here is 0.3 amps, and the resistance here is 10, well, shouldn't we be able to figure out exactly how much voltage this takes up? Yeah. Current multiplied by resistance, Ohm's law. So we've got our 10 ohms, 10, right? Jot this down right here in the corner, 10 ohms. We've got our current that we already know, 0.3, multiplied by 0.3 amps. 10 multiplied by 0.3 equals 3 volts. Okay? 3 volts, boom, there goes the 6 volts. So if you do have two resistors here that are not equal to one another, then the voltage will not be split in half. It's going to be split proportionally. You'll use Ohm's law just like I did right there to determine how much voltage is going through it. If they are the same, if you get like 20 ohms right here and 20 ohms right here, congratulations, that's less work you have to do. Just split whatever voltage was coming into this line in half, and you're done. Okay? Now the last one is power. This one's pretty easy as well. It just involves a different equation. The equation that's used for power, and again, this is in the notes, and we've talked about this in a couple of the videos, is that power is equal to current multiplied by voltage. So anytime you want to find out how much a resistor, how much a lamp is using in terms of power, what is this electricity doing to provide power into this resistor? From there, you could figure out, for instance, how much heat is coming off the resistor or how much light is coming off the lamp. In this case, we just want to stick with the power. How much power is being provided to this specific part of the circuit? You take whatever current is flowing through that part and whatever voltage is being supplied to that part, and then you can find out power. Okay? Pretty straightforward calculation. In this case, let's just take one of these pieces right here. Okay? We've got a resistor This resistor has 0.3 amps moving across it, and 3 volts. Current multiplied by voltage is equal to power. So if it has 0.3 amps going through it, multiply that by the voltage, which is 3 volts going through it, 0.3 times 3 is 0.9. 0.9 watts. That's how much power is going through it. 0.9 watts. Now, 0.3 times 3 is the same one here, so again, it's 0.9 watts. For the final one, it would be 0.6 times 6 volts, which would be 3.6 watts. And finally, the total current moving out of the battery is 0.9. The total voltage coming out of the battery is 6. 0.9 multiplied by 6 is 5.4 watts. That's the total problem. Punch those numbers in, I checked them on my website, I got all of them correct. Okay? It seems like it's a lot, but you're just using this equation, right? Simple multiplication division, and this equation right here, again, straightforward multiplication division. Numbers shouldn't be too tricky. If you have any problems, please, again, feel free to reach out to me. I'm always more than happy to help. But I hope showing you how I would work through one of these problems will help to make it a little bit easier for you to do these two as well.